Good morning. Hello students. Today I am going to cover BSc fifth semester syllabus Mathematics Paper 1 Real Analysis, which is syllabus of Karnataka University Dharwad. Unit 1 Riemann Integration. I am Dr. Krishna P. Chavrati, Government First Grade College, Naragon. Today I would like to start with the properties of R integral, which is continuation of the previous session. So also would like to discuss some properties of R integral. So first let us see the first property in this session. So f and g are integrable functions in closed interval AB, and f of x should be less than or equal to g of x for all x belongs to closed interval AB. Then we have that relation integration of f of x should be less than or equal to the integration of g of x dx. And proof of this theorem is, since these two fx and g of x, fx should be less than or equal to g of x for all x belongs to closed interval AB. Since f and g are integrable in the closed interval AB, then this difference of this magnitude of this difference f of x minus g of x is also R integrable in AB. Hence, for every mode of division d of AB, and the magnitude of d should be less than or equal to delta, and for every choice of delta, choice of xir in this interval xir minus 1 comma xr, we have that here limit of the summation of g of xir minus f of xir with the delta as n approaches to infinity, where r is running from 1 to n is running from n is tending to infinity. So that equal to that is the integration a to b of g of x minus f of x, and g of x integration and f of x integration. Since g is greater than or equal to f for all x belongs to this here, so definitely this left hand side is obviously it is greater than or equal to 0, and it is also greater than or equal to 0. So obviously it becomes here finally integration of f of x dx should be less than or equal to integration of g of x. So also I would like to discuss one lemma which will be helpful in deriving the next theorem. The oscillation of bounded function f of x enclosed into AB is the supremum of the set of number. So magnitude of f of alpha minus f of beta, where alpha and beta belongs to the member of A and B. So let capital M and small m be the bounds of f of x in the closed interval AB. So we have that infimum should be less than or equal to f of alpha, and supremum should be greater than or equal to f of beta for all alpha and beta belongs to closed interval AB. Then we have that magnitude of alpha minus b f of beta should be less than or equal to supremum minus infimum. So that now let us see that theorem 7, integrability of the modulus of function. Suppose fx is bounded and integrable in the closed interval AB, then magnitude of f of x or modulus of f of x is also bounded and are integrable in closed interval AB, and hence magnitude of integration of f of x dx should be less than or equal to the integration of the magnitude of f of x dx. So let us see the proof of this theorem. Since f is bounded in closed interval AB, by definition, then there exists a number k belongs to closed interval AB such that magnitude of f of x should be less than or equal to k for all x belongs to closed interval AB, taking the magnitude again there on the both sides, so that definitely magnitude of f of x or modulus of f of x is bounded in the closed interval AB. This is the part of boundedness. Now let us see that is the part of that is the integrability. Let D be a division of AB. Let capital MR prime and small mr prime be the bounds of f of x, and capital MR and small mr be the bounds of magnitude of x or modulus of x in the closed subinterval xr minus 1 comma xr. Then we choose that is the for every alpha 1 and alpha 2 are the members of subinterval xr minus 1 comma xr. We have the relation is magnitude of the individual magnitude difference is less than or equal to the magnitude of the f of alpha 2 minus of alpha 1. Therefore, by above lemma, we can write it this as capital MR and this as small mr, and this should be mr prime and small mr prime, taking a summation with the delta r, and then since fx is integrable in closed interval AB, then ultimately that left hand side should be less than equal to less than epsilon. Then obviously this right hand side is also less than this. And so this implies magnitude of x or modulus of x is R integrable in closed interval AB. Hence, modulus of f of x is bounded and R integrable in the closed interval AB for all x. Then we can see that this fx should be lies between this interval. And also since f and this magnitude of x are integrable in closed interval AB, then we can write it this integral values lies between this magnitude there. So integration of the magnitude of x with a negative and positive there. So obviously we can write it that is the modulus of the integration of f of x should be less than equal to the integration of the modulus of f of x dx. Now let us see the remark based on that theorem. Previous theorem. The converse of the above theorem, it is not true then. Now let us consider the magnitude function then. When a magnitude of x, it is 1 when x is rational, when it is minus 1 and x is irrational. So, but it is a bound at that because since it is minus 1 and plus 1 value, so that fx is bounded in closed interval AB. But it is not R integrable over closed interval this AB. Let T be a division of AB. Then each of the subintervals xr minus 1 comma xr, we have the supremum and infimum different values 1 and minus 1 respectively. Obviously, UPF and LPF are different values. Ultimately, that and upper integral and lower integral are reverse nature in that, so that these two are not equal to each other, upper integral and lower integral, so that this f of x is not R integral. So, but this is bounded for all x, so that this value is b minus a, because since it is a magnitude, it is R integral. But converse need not be true then. So only it is at right hand side it is true, but left hand side it is not true. So that's why it is not R integrable in that. So now let us move on to the integrability of the sum of two functions is again R integrable, since suppose these two are bounded and are integrable in closed interval AB, then fx plus gx is also bounded and are integrable in AB. First, let us see that since f and g are integrable, bounded, and then there exists a boundedness, register number k belongs to R, magnitude of such that magnitude of x should be less than or equal to k, and magnitude of g of x should be less than or equal to k for all x belongs to closed interval AB. So now let us construct this here. So by taking magnitude of fx plus gx less than or equal to the individual magnitude, ultimately obviously it is a bounded fx plus gx is bounded in closed interval AB. It is a part of boundedness, but now we can say that R integrity. Let T be a division of AB. Let mr prime, small mr prime be the bounds of fx. Mr double prime, small mr prime, double prime be the bounds of g of x, and mr, small mr be the bounds of fx plus gx in the subintervals xr minus 1 comma xr. Then we have alpha 1 and alpha 2 belongs to the subinterval. We can have that this relation here. This is the f of alpha 2 minus f of alpha 1, and this fx plus gx is by taking where alpha 1 and alpha 2 are the members of subinterval, we can write it fx plus gx like this form. And that should be less than or equal to, this is what we have, that f of alpha 2 minus f of alpha 1 plus g of alpha 2 minus g of alpha 1. Therefore, by above lemma, we can make use of this is f of alpha 2 minus plus g of alpha 2, it is capital MR. This is capital MR, this is small mr. So then ultimately it is capital MR prime minus small mr prime, capital MR double prime, small mr double prime, by taking a summation throughout with the delta R. Since fx and gx are integrable in the closed interval AB, then we have that is this is epsilon by 2, this is epsilon by 2 as our convention. Therefore, we plug these relation in the equation 1. Ultimately, this summation should be less than epsilon. This is a fx, this is a gx. So sum of f plus g is R integrable over AB. Hence, fx plus gx is bounded and R integrable in closed interval AB. Similarly, we can prove that integrability of difference if suppose f and g are bounded and are integrable in closed interval AB, that difference fx minus gx is also bounded and are integrable in the closed interval AB. So let us see the proof of these two as similarly exactly as we have seen in the previous theorem. So fx and gx are bounded in closed interval AB, then there exists a number k belongs to R such that we can use this definitions of boundedness of f and g are there. So just we can take it here fx minus gx. Ultimately, it is the integer magnitude, it becomes a plus, so that ultimately it is fx minus gx is also bounded in the closed interval AB. So also we prove that this fx minus gx is also are integrable in the closed interval AB. That D be a division of AB and mr prime, small mr prime with be the bounds of fx, mr double prime, mr small mr double prime, and capital Mr, small mr be the bounds of g of x and fx minus gx in the subintervals xr minus 1, xr. Then we have alpha 1 and 2 are the members of xr minus 1, xr. We have that. Again, we can write it fx minus gx just alpha 2, gf alpha 2. And this is what, just rewrite this as good as this is what we have there. So ultimately, this is just to be do the algebraic some simplifications by taking above lemma, so that we can write it. This is capital MR, this f of alpha 2 minus f of alpha 1 capital MR minus gf alpha 2 minus gf alpha 1 is capital. This is what small mr, and this is what the capital MR double prime MR. This is MR double prime. This is capital MR prime. This small mr, and it is capital small MR double prime. So obviously we have a simplification like with by taking the summation with the delta on both sides. So since f and g are integrable in the closed interval AB, then we have these two are respectively epsilon by 2, epsilon by 2. Plug in these relations in equation 1, we get that relation is less than epsilon. This is a fx minus small mr is gx. This difference is also R integrable. Hence, fx and minus gx is bounded and are integrable in the closed interval AB. These are the references we have followed in this session. Thank you.